5.2, the natural logarithm function integration. We're not going to integrate natural logs. It's kind of what the title sounds like. That's not what we're doing. But we're actually going to take one of the properties that we learned last time, namely what the derivative of natural log is, and we're going to use it in reverse. So that antiderivative sheet that I handed out, this is going to be, I think it's property or rule or whatever, 12 on the antiderivative sheet. And this is what it says. So when we did the derivative of the natural log of x was 1 over x, right? That's what we defined it to be last time. Therefore, if we then take the integral, right, like this, we will have the following integration property. The integral of 1 over x is the natural log of the absolute value of x plus c, of course. Okay, why is there an absolute value? Does anybody remember how natural log is defined? Yeah.
I just didn't blank. The x cannot be negative because it messes up the graph.
Right. So the natural log of x, its domain, which might be the word you're looking for, its domain is only positive numbers. Okay? We already don't have to worry about 0 because 0 is not in the domain of 1 over x anyway. So that's taken care of easily because it's also not in the domain of natural log of x. But we could have negative numbers underneath the division sign. That's not a problem, but we can't have them inside of a natural log. So those absolute values are going to keep showing up. That's probably the most common thing people forget when they're working with these. So I'm going to hit it multiple times today and remind you we need absolute values, we need absolute values. There are some cases where we don't. We'll see an example, and when we do, I'll make mention of why. Okay? But generally speaking, we need them. Okay, so we're going to do some examples. The first one is a super straightforward example of this property. Any idea what the derivative of 5 over x, antiderivative, meant to say, of 5 over x would be? There's clearly an over x part, right? So we're going to get a natural log, we're going to get an absolute value of x. That part's going to happen, and we're going to get the plus c. What's going to happen with the 5? Where should it go?
Is it just in front?
It's in front, yeah. So it's actually a constant multiplier. And if it helps you, you can think about this or remind yourself that this is the same expression, but expressed differently. It's 5 times 1 over x. Okay, so again, a common mistake here is to put the 5 inside with the x. It's not inside, right? It just isn't. It's a constant multiplier, and constant multipliers come along for the ride. So x in front, 1 over x becomes natural log, absolute value of x. Okay? Do you want to go back to logarithmic differentiation, or are you good? I thought so. All right, so we'll keep going with this one. All right. A little bit different than the last one. On this one, we actually see addition and subtraction in the denominator. Okay, so this is going to take us back to section 4.5 in Calc 1. Does anybody, off the top of your head, remember the last thing we did in chapter 4 in Calc 1? Huh? We did U substitution. Y'all remember that? Oh, Levi's like, no, I don't know what you're talking about, U substitution. Okay. All right, it would be really nice. It'd be really nice if that denominator was just x, wouldn't it? Of course it would. So we're going to make it be that way by using U substitution. So we're going to say that the U is the denominator of 4 minus 3x. Okay? So we're going to use U substitution a lot today. You're going to get really good at it. All right. And then the next thing we do is we take the derivative of what's there. What is the derivative of 4 minus 3x? Negative 3. And then technically this is du dx, by the way. But we don't usually write it that way. We usually we'll eventually have to move it to the other side anyway. So we tend to write it that way to start. So the dx is necessary on the side. That's what's going to allow the substitution that we need in our problem. So we have negative 3 dx. Okay, we don't have a negative 3 actually standing alone by itself in our problem, agreed? I mean, there's a negative 3 there, but it's attached to it's not where it needs to be. So what we do is we divide both sides by negative 3, or that would be equivalent if you prefer, to be multiplying by 1 over, or negative 1 over 3, or 1 over negative 3. Okay, so all that looking familiar now. All right, so why are we doing that? We're doing that to change this expression into something that looks more like number 12 on the antiderivative sheet, namely integration of 1 over x. So in particular, the part that's in the denominator is now u. The one on the top stays the same. The dx at the end is replaced by negative 1/3, which we will put at the beginning here, and dx at the end. Now you could put the dx on top or whatever too, it doesn't matter. I just end cap it. I always have the integration at the beginning, that symbol, the s symbol, and the dx at the end. du is what I meant. I'm getting a look. Thank you. Du at the end is what I meant. Thank you. Okay. All good? Does it look like property number 12 now? It does. I've still got a negative 1/3 at the beginning. That's fine. What's the antiderivative of 1 over u? Natural log of absolute value of u, right? And always a plus c. But I'm not done. Why not? Yeah, if the problem started out with x, the problem needs to be ending with x. Okay, any substitution we made in between, we have to undo it. So, or back substitute. So I've got negative 1/3 natural log, and then the u is 4 minus 3x, which is in our absolute values, plus c. So far, so good? Yes, sir.
I know that u substitution works, and so I can intuitively see why u substitution is needed. But why can't we just do what we did for example A? I know it'll give us the wrong answer, but why is that?
Because there's a chain rule here. This is what happens when we're doing u substitution is we have a chain rule.
Yeah.
So the underneath part of our division, right underneath of our fraction, is actually a chain where it's got an inside function. And we have to undo the fact that we would, if we were taking a chain rule and doing a derivative, we'd have the derivative of the inside. So we have to undo the derivative of the inside. And that's what u substitution does. Exactly. So u substitution is really a reverse chain rule process. It doesn't work on everything, but it's one of the very few tools you guys have right now is u substitution. There's one other tool you have, and we'll see it in play in a little bit too. So this problem actually looks worse than the one before, but it's actually not. Okay? So when we did the problem before, we identified that the denominator, and because of the section we're in, we kind of know this to be true to some degree as well, that we're looking at things that are going to have 1 over x's in them, by and large. There's going to be a couple examples later that they're a little different. But the thing that tells us that the u substitution needs to be the denominator is there's two things. Number one, if you let u be what's on top and the u goes on top, you don't have any way to get rid of the stuff on bottom, and that's not good. So that's one issue. Secondly, the degree of this denominator is 3, right? And the degree of the numerator is 2. So when you take the derivative of the denominator, you at least stand a chance at it becoming something that looks like the numerator, because the degree will become what the numerator is when you take the derivative. So we are going to start, our default right now is going to be that we're going to let the denominator equal u. And we're going to take its derivative. So what's the derivative of x cubed minus 3x squared? 3x squared minus 6x, and then I have dx on the end. Okay, that's not exactly my numerator. But how could I manipulate it so that it does look like my numerator? Take a 3 out or divide by 3. And so it becomes a lot like what we did, actually it was this one over here, where we're going to divide the other side, well both sides, but we're going to divide the 3 and move it to the other side. So in a very real sense, these are all going to be divided by 3 as well. So I'm going to do 1/3 du. And I'm going to actually divide each of those pieces, which is going to give me my x squared minus 2x dx, which is what I see in my numerator. So this piece here matches this piece here, which means it can be replaced now by the 1/3 and the du. So the 1/3, I always write them in front because it's just going to be a constant multiplier. It doesn't get affected in any really complicated way by doing antiderivatives. And I have the du at the end. And then my u is again in the denominator because the entire denominator is what I identified as my value for u. I made that substitution remark. So now we have 1/3. What's the antiderivative of 1 over u? Natural log, absolute value of u. I don't leave it with u's in it though. I change it. And what does u equal? X cubed and minus 3x squared. Okay, so far so good? Yep.
Why is it 1 over u now? Is it cancel out there?
Yeah, let me make that mark or comment on here. I can do that. So if you take a look right here, this piece is what I let u be. And then the antiderivative of the u goes here, right? So the natural log of u is what shows up. And then I put it back in for what u is equal to. So it's a substitution, back substitution. I feel like maybe that's not the question you had then. Sorry.
How did you get a 1 over u? Like, how did you bring up that x?
Oh, because this piece right here was in the denominator, so the u replaced what was in the denominator, and the yellow part that I highlighted was replaced by a 1 on top and the du at the end. Yes. Okay. It's okay? Okay, take a look at the next one, number 1D. In what ways is it different than C? Because we are not going to be able to do this one in the same way. How is it different?
Higher degree.
The higher degree is on top. So if I take the derivative of the denominator, I'm not going to be able to get what's on top. Like that's not going to work like it did on the last problem. But if I let u be what's on top, why in the world would the part that's on bottom go away, right? What that means is u substitution is not going to work for this particular problem, at least not at the outset. So you need another technique, and it's a technique we have not done a lot, but we did it maybe just a tiny bit in Calc 1. And I'm going to show you again how you do this. And again, this is algebra that you haven't done in a long time, but it's an algebra topic, and it's called long division. Oh, yeah. Way back when. And I know it's an Algebra 1 topic because I've done it recently at home with my 9th graders, just so y'all know. They weren't fans of it either. All right, so we're going to take the 2x squared plus 7x minus 3, and we're going to divide it by x minus 2. Okay, long division with polynomials is actually easier than long division with numbers because everything goes in perfectly until you get a remainder at the end. That part's really nice because long division with numbers doesn't do that. So here's the way that we think about this. We always look at the first pieces and we ask ourselves, what do I have to multiply, in this case x, by to get 2x squared? 2x. And we're going to write that 2x on top. 2x. And then we're going to actually multiply 2x by what's in front of the division house or whatever. So I have 2x squared and I have minus 4x. Lining them up appropriately. If you had missing terms, like if this started out 2x cubed and there was a missing an x squared, you'd put a 0x squared in as a placeholder. Y'all remember that? That could be a nuance that could come up. And then we change signs. So we subtract, we change our signs. So these two cancel out, which was the whole point. The first piece, if you've chosen properly, will always reduce to 0. And then you have what's left in the second piece. So now I have 7x plus 4x, which is 11x. And minus 3, and I repeat the process. I ask myself, what do I have to multiply the x on the outside by to get 11x? And the answer is 11. So we put plus 11 up here, and we multiply to get 11x and minus 22. And again, we change our signs. Again, if done properly, these add to 0, which they do. And now I have negative 3 plus 22, which gives me 19. Okay, how do I know when I'm done? Do you remember?
Can there be a remainder?
Okay, there's going to be a remainder. My remainder is going to be 19. How do I know that I stop right here and I don't try to do it again?
There's an X.
Yeah, so it has to do with the degrees. So you're identifying the X as the piece. The degree on 19 is actually degree 0. Constants have a degree of 0, right? The degree on the X over here is a degree of 1. So if the value on the outside of the division house, if you will, has a higher exponent than what you have underneath, then you're done. So we haven't actually done any calculus yet. I know that's kind of discouraging. But what we have found out is that this can be rewritten as 2x plus 11. And then I have, was it positive? Yes, positive 19 over the same denominator started with x minus 2 dx. So what's the antiderivative of 2x? X squared, right? What's the antiderivative of the 11? 11x. What's the antiderivative of 19 over x minus 2? Okay, we're going to bring the 19 out. Then what? Natural log, absolute value of x minus 2. There should be something in your mind that says, I feel like there's a chain rule there. It has addition and subtraction. And there kind of is. It's just a very unexciting chain rule. If you were to let the u be what's underneath there at x minus 2 like that, what would the derivative of that be? 1. So we can kind of get away with not having to deal with the chain rule part of this because its derivative is 1. So we kind of get to avoid that just because of that. Now eventually, when it's linear, you're going to be able to deal with it without writing the chain rule down anyway, because you're going to see enough of them that you're going to recognize when that shows up and what to do. I don't think we're right there yet. I'm going to keep writing them. But on this one, I avoid the chain rule simply because the derivative is equal to 1. So this would be what I'd have for my antiderivative. Okay, you ready for another one? What's interesting about this? There's a log in it, first of all, and it's squared. Actually, both of those things make it a little interesting. Most interesting about this should be the fact that you don't have any derivative right now. Didn't say that right. You don't have any antiderivative right now for log. That's not a property we've discussed. We will, but not today. What that tells you is that if you see log in your problem, then u is going to equal that value. Because if I can eliminate it with a u substitution, then I never have to take the antiderivative of it. Are you with me? Now, I don't need the squaring part of it. It's just natural log of x. That'll be just fine for what we're doing. You might be tempted to think, can I bring the 2 in front? You can't. That property for logs applies if the 2 was on the x only. Like if it said natural log of x squared, it doesn't say that. The whole natural log is being squared. Okay, so resist the urge to move the 2. It's just going to stay put for the moment. But what is the derivative of the natural log of x? 1 over x dx. Why is that friendly? That's the other part of the problem, the part you probably wanted to let u be to start with because, or at least thought you were going to deal with, because it was there as a denominator, right? So in some sense, if you're not seeing this right now, let me rewrite this in a different way. This is the natural log of x squared. And we could write it as times 1 over x dx. Dividing by x is the same as multiplying by the reciprocal, namely 1 over x. Okay, are we good? Okay, we can now eliminate these pieces. In particular, the natural log of x is u. Don't forget the squared, it's still there. So that gets replaced. The 1 over x dx will get replaced by du. Okay. And now we can actually take an antiderivative that's quite familiar to you. What's the antiderivative of u squared? U cubed over 3, right? Plus c. Don't forget them. Gotta get the plus c in there. I don't want to leave it this way, of course. My u needs to be resubstituted back, and I do need the parentheses around the natural log of x. It is the entire natural log of x that is being cubed. And so for the very same reason that we can't move the 2 at the beginning to the front, we can't move the 3 to the beginning here either. But I also don't want it written as the natural log of x cubed without the parentheses. Otherwise, it means something different, right? The understood meaning is that the x would be what's being cubed and not the entire expression. So those parentheses are necessary. Okay. We have a whole bunch of new antiderivative rules. Your antiderivative gateway is not for quite some time, but at the point when it does come around, these will be on the list of things that you will need to know antiderivatives for. We're going to add to it a little bit. So these are trigonometric integrals. So if you'll remember back in Calc 1, we only had these first two. We knew that the antiderivative of sine and the antiderivative of cosine had this oscillating feature. Those are the only two that we did in Chapter 4. And we kind of just said, you'll learn the rest of them in Calc 2. Well, that's today. So we have 4 other antiderivative rules. One for tangent, for cotangent, for secant, and for cosecant. And there's some patterning here that if you would recognize what they are, might help you to memorize them later. Again, we've got some time before an antiderivative quiz. So jot those down here now. And then later after class, you can transfer them over to your antiderivative sheet that I gave you today as well. Okay? Okay, does everybody have them all? I'm going to switch my screen just yet in case we're still working. Are you good, Anna? Okay. Sorry, I'm looking at pencils moving, so if your pencil's moving, that's why I just want to make sure that you're good. Okay, cool. All right, we've got a couple examples with these. Taking a look at this first one, you see secant, and this is not a very exciting chain rule, but it is a chain rule because it's not just secant of x, it is secant of x over 2, okay? So the u substitution, this is again one of those places where eventually when you see this, you're not going to need to write the u substitution down. You're just going to know exactly what's happening here and be able to accommodate for it quickly because it's not a very exciting u substitution. But for right now, while we're still getting our feet wet again with u substitutions, I'm at least going to write them down. So our u value is going to be the x over 2 that's inside. So what is the derivative of x over 2? 1/2. And then dx, right? Now, I don't have a 1/2 in the problem, so I need to move this 1/2 to the other side, and I do that with multiplication. So 2 du is equal to dx. So as I come back here and I rewrite, my dx is going to get replaced with the 2 at the beginning and the du at the end. The x over 2 is going to get replaced with u. But notice we didn't do anything with secant, so the secant is still there. But now we can use one of those properties that we just had on our previous slide. So we have the 2 at the beginning. What's the antiderivative of secant? It's got a natural log in it of what? Secant of u plus the tangent of u. And then I have my plus c, right? And then my last follow-up step would be to put the u's back in as x over 2's. So I have 2 natural log of secant of x over 2 plus the tangent of x over 2 plus c. Okay, so if we don't have to memorize them at the moment, this is not difficult to apply them, right? A lot of the same techniques as we were doing in the other problems. On this one, let me make one comment first. If this were the reciprocal, right? If I actually had the addition piece on top, I might be able to do something with trig substitutions, right? With things like the fact that sine over cosine is tangent and stuff like that. I'd stand a chance at working with some of that. But because the addition is on the bottom, I can't do a trig substitution to make that work. Are you with me? The addition or subtraction being on the bottom means there's no way to separate this nicely. If I had the addition and subtraction on the top, I could separate fractions out. I can't separate fractions if addition's on the bottom. What that means is that trig substitution's not an option for this particular one, which puts me right back into the point of doing u substitution because I don't have any other techniques. So my u substitution will be the entire denominator, 1 plus sine t. What is the derivative of 1 plus sine t? Cosine t dt. For what you do for me, if you change t's into x's, t's not my favorite variable to show up in problems, but it happens from time to time. If you change them into x's, I'm fine with that. WebAssign will not be fine with that. So if you're getting what you're sure is the right answer, you might want to double check your variables because it will fuss at you if you change variables around. But if you change it on a quiz or a test or something like that, for me, I don't care, or written assignment. Okay, we have cosine t dt in this problem, right? So the problem looks much like the ones we've done before at this point. We have 1 over u du. It's not even a very exciting one, right? Antiderivative of 1 over u, you know it. Natural log of the absolute value of u plus c. U is 1 plus the sine of t plus c. Now, there's nothing wrong with the particular way that this is written, but it's at least worth mentioning that we could see this written and it would be correct without the absolute values. It'll still have to have parentheses. But why would the absolute values not technically be necessary on this problem?
Sine only takes positive representatives.
Close. It does get it doesn't take. Let me stop for just a second. You're reading output values. The output values of sine aren't just positive, but what are they?
1 to negative.
1 to negative 1. And we're adding 1. So the smallest value that sine could be, remember your sine curves look like this. And they go between 1 up here and negative 1 down here. So the smallest value that sine could be is negative 1. And we're adding 1, as Tanner pointed out over here, the plus 1 here. Now, that doesn't eliminate the fact that 0 is not allowed, but absolute values don't actually fix that either. But everything else that's bigger than negative 1, when added to the 1, would already be positive. So there's nothing wrong with leaving the absolute values on, But if you see them removed somewhere, understand that that's the reason why sometimes you can do that. There are other problems where you could see that as well. Like let's say, for instance, that you had the natural log of x squared plus 3. Well, x squared is always positive. Plus 3 makes it even more positive. I don't really need absolute values around that. So if I were to leave them off, it'd be correct. The default should be to put them on. Okay, I'm not saying you don't have to care. But if you see them, then that's probably, if you could examine what you're actually removing them from, there's probably a reason why. Okay, last problem. You ready? Okay. Definite integrals. What does definite mean? Yeah. When we see the phrase definite or the word definite, it means there's limits of integration. It also means that the answer at the end is going to be some kind of a number. It won't have any variables left in it. Okay? We don't really do anything different through the process in the middle of it. But at the end, we have to do the fundamental theorem of calculus, and we have to evaluate those values that we got at the particular limits that we were given. So, taking a look at what's here, ignoring the purple marked pieces at the moment because we don't need them, what process are we going to have to use to find the antiderivative? U substitution. And in particular, it has to be U substitution. Why? Because we see a natural log. And we don't have any techniques for taking antiderivatives of natural logs, which means whatever piece has the natural log in it must be the piece that we're identifying as U. So U is going to be not just natural log. What would be a little more helpful? The 1 plus part. And not only is it helpful just from the sense of replacing it, but the derivative isn't any different whether the 1 plus is there or not. So it's a very helpful step to do to replace the entire thing with the U. What's the derivative of 1 plus natural log x? 1 over x dx. Which is exactly in our problem as well, right? This over x part and this dx part are going to get replaced by du at the end. I don't even have a constant multiplier or anything to worry about. I don't have a denominator anymore. I have a u, but what else do I have? A squared. This is u squared. Okay, antiderivative of u squared, we did that one earlier. U cubed over 3, right? Now, let me make one comment because I forgot to make it before. You'll notice that I didn't put the limits of integration here when I rewrote it. So I pay a lot of attention to making each step sequentially equal to the next step. That's something I'm really careful about. Why would I have left them off? Because it was intentional. I purposely left them off. Any ideas? Okay, so between the problem we began with and the problem I changed it to, I changed my variables, right? Those numbers that I was given at the beginning apply to the variable x. They're not values for u. So I left them off on the step where I changed it into u. But my next step, when I turn it back into x's, I will be able to use them exactly the way they were. So this is now, 1 plus the natural log of x cubed over 3. And now I can evaluate them at the number e and the number 1 like this. Okay, so the numbers e and 1 are in the steps that have x in them, and they're not in the steps that have u in them on purpose. Now we're going to evaluate at e, and we're going to subtract that from that we're going to subtract the evaluation at 1. So I have 1 plus the natural log of e cubed over 3 minus 1 plus the natural log of 1 cubed over 3. Correct? Okay, that's the fundamental theorem of calculus. But as we talked about last time, what is the natural log of e? That's 1. What is the natural log of 1? That is 0. So we're going to do some arithmetic simplification. 1 plus 1 is, cubed is 8. So the first fraction is 8/3. Second fraction, 1 plus 0 is 1. Cubed is 1. And then I've got that divided by 3. So 8/3 minus 1/3 is 7/3. And I want to show you and remind you, because we have time, I have 5 minutes, which is not enough time to put you at boards, but it is enough time to remind you of one more cool trick in your calculator that you may have forgotten. So we're going to do that. So grab your calculator out. I'd like for you to put the original expression that you were given and told to take the antiderivative of. So 1 plus natural log of x, quantity squared, over x. Put that in y1. I'm going to remind you of 2 different ways you can verify a definite integral with your calculator. Okay, 2 ways. Both of them hinge on you putting this in y1, at least conveniently so. So do you remember the other calculator thing we did earlier? It was math, which one? 8. The one we're going to look at right now first, the first way we're going to do this is math 9. So back in your regular screen, I want you to hit math 9. My version of math 9 probably doesn't look like any of yours because I have an older calculator. It says F and I and T. Yours says like this. I think that's what it does. Is that right? Okay, I remembered it right. Cool. So clearly, on your limits of integration, I'll do yours first, and then just for the purpose, in case any of you have mine, I'll do it second. It'll look just like what's on your screen. So it's going to go 1 down here. I'm going to put an E right here. I put y1 here because we saved it in y1. Remember, that's vars, y vars function y1. And I put an x over here. My version, I tell it y1, comma x. I do my lower limit of integration and my upper limit of integration. So y1, x1e, all with commas between. If you're wondering how to get E, you can do second division sign, like the division symbol, that's one way. Or you can do second natural log and put the 1 after it. That's another option. It gives me 2.3 repeating. You may recognize that as equal to 7/3, but at some point you're going to get some ugly decimal that repeats and it's not going to look like something you know. So if that happens, if you hit math, the first option there is, it's got an arrow and it says frac. And if you click on it, it will turn the previous answer into a fraction. There's 7/3. Okay, option number 2. This is always for the visually appealing folks. Make sure that your window, I think our window we had before is 0 to 10. 0 to 10 will work probably. Let me just graph and see. Yeah, it'll work okay. It's not excellent, but maybe we can make it a little bit smaller. We're going from 1 to E. So 0 to 5 would be far enough if you wish. So you can make your x go from 0 to 5. I'll give you a slightly bigger graph. Okay, so it's a funny looking graph. It looks like, try again. Mine looks something like this. Yours looks something like that? Okay, so I want you to hit second trace. That's the calculate menu. Option number 7 looks like an integral, so choose number 7. Lower limit, that's the number 1. Upper limit, that's the number E, so second division sign. Remember, it shades it in, which is lovely, and it tells you that same 2.3 repeating at the bottom. Okay. The downfall is that I don't know of any way that you can take the 2.3 right here and then turn it back into a fraction the way we did in the other screen. So if it's got something like that, that's not super helpful. But do y'all remember how to do these things? Remember we did these before? That's your refresher. All right, so the homework for this section is now done as well, or due as well.